All right, in this video here, we're going to talk briefly about the graphs of inverse functions and the relationship that they have with each other. Right, so the graph of f inverse is obtained by reflecting the graph of f in the line y equals x. Right, so recall the line y equals x is the diagonal line that goes through the origin, where every point on that line, the x and y coordinates are exactly the same. Right, y equals x, so those two are the same values. Right, so that's the line y equals x. So if I have the graph of a function f up here, this is the one that's up here. Right? If I want to get the graph of f inverse, I just take the graph of f and just kind of flip it over that diagonal line, and that gives me the graph of f inverse. Right? So the graphs of inverse functions always have that relationship. They're always reflections across that diagonal line. Right? Now, why are they reflections across that diagonal line? Well, if you watch some of the other videos that I did about inverse functions and what the inverse of a function is, remember, inverse functions, they switch, they're opposites of each other. They switch inputs and outputs, right? So if I do f of 5 and it gives me 2, if I do f inverse of 2, it gives me 5, right? It switches the input and the output, which means when we're talking about the graph, it switches the x and the y coordinates, right? And again, if you haven't seen the other videos that I did about inverse functions, you might want to check those out, where I say the same thing I just did, but in a lot more detail and with more explanation. But assuming you watch those and you understand that, it would make sense then that inverse functions, the graphs of them, are reflections over this line y equals x. Right? Just to give a couple examples, just to put some numbers in here. Let's say that this point up here on the graph, and I didn't put any marks there, so I'm just going to put some random numbers up. So let's say that this is the point -2, 2. Right? Left 2, up 2 to get that point on the graph of f. Well, the corresponding point on the graph of f inverse, I'm going to switch the x and the y. It's going to be at the point 2, -2. Right, so if I switch the x and y coordinates of this point, it gives me a point on the graph of f inverse. And if I switch the x and y coordinates, well, that's just reflecting that point across that diagonal line. Right, these 2 points are the same distance from that diagonal line there. Right, to do another point, let's say this point up here that's the y-intercept, so it would be 0, let's say 3. Right, so that's a point on the graph of f. If I switch the x and y coordinates, which is what an inverse function does, I get 3, 0, which gives me this point over here, which is the x-intercept of the graph of f inverse. And again, those 2 points are reflections across that diagonal line y equals x. All right, one more, just because it's kind of fun to put points on a graph like this. I'm having a good time here. So this point up here, let's say that that's the point 3, 5. Right. So let's say that's the point 3, 5. Well, that's the point on the graph of f. For the graph of f inverse, I switch the x's and y's, I switch the inputs and the outputs, so I get the point 5, 3, which would be somewhere up in here. Right, that's my point 5, 3, which again is a reflection across that diagonal line. All right, so if you understand inverse functions, they switch input and output values, they switch x and y values, well then it would make perfect sense what we're saying here, that the graph of f inverse is just the reflection of the graph of f over that line y equals x. Right, that line where x and y are the same, if I switch every x and y value, I just reflect the point to the other side of that diagonal line. All right, so that's a property of the graphs of inverse functions, which applies to any pair of inverse functions. The graphs are always going to have that relationship in terms of that diagonal line y equals x.